Welcome to FMTV 122, Sound Theory and Practice 1. Now we can move into the third property of sound, quality. When we were looking at pure tone, we were looking at sounds that had one steady frequency at one steady amplitude. A sound like this doesn't really have a distinct quality. No matter what device is generating that tone, it will sound the same. It's only when we get into the more complicated real-world sounds, where many frequencies occur at a variety of amplitudes, and those frequencies and amplitudes shift over time, do we really need to look at quality. When we look at a sound that has many different frequencies within it, we can compare those frequencies to each other. To begin, we find the lowest dominant frequency in the sound, and we label that frequency the fundamental frequency. This is also called the first harmonic frequency. Every frequency in that sound that has a higher frequency than the fundamental will fall into one of two categories: overtones and harmonics. Harmonic frequencies have an exact integer relationship with the fundamental frequency. This means that the frequency in hertz of the first harmonic has been multiplied by an integer, a whole number. If we had a sound whose fundamental frequency was 100 hertz, then the second harmonic frequency in that sound would be 200 hertz. The third would be 300 hertz, the fourth would be 400 hertz, and so on. When a sound is made of primarily harmonic frequencies, humans tend to experience this in a positive manner. We like the sound of harmonic frequencies playing together. The other category, overtones, are all the other frequencies that don't have that integer relationship with the fundamental frequency. So if the sound in our example also included a 125 Hz tone and a 160 Hz tone, those would be considered overtones because you cannot multiply the fundamental frequency by a whole number to get them. Humans tend not to enjoy listening to collections of random overtones. These sounds can seem grating and make people feel a bit uneasy. As filmmakers, we can use this to our advantage. When our protagonist enters the scene, we can play a bit of music consisting of harmonic frequencies, and this will make the audience feel good about the person they're seeing on screen. Conversely, when the antagonist arrives, we can have them accompanied by a jarring collection of overtones that put the audience on edge, and they will associate that feeling with the character. Of course, we can use this in far more subtle ways as well. Along with harmonics and overtones, another aspect of quality is timbre, not to be confused with the word timber, which is what you call out if you're chopping a tree down and it's about to fall on your friend. Timbre is a bit of a blanket term, and you'll sometimes hear it referred to as sound color. It is the collection of unique sound elements that help distinguish one sound from another, even if those sounds contain the same fundamental frequency existing at the same amplitude. One element of the timbre of a sound is the attack time of a sound. This is the time the sound takes from when it began to when it reaches its peak amplitude. With most sounds, the attack time is followed by the decay time. This is a decrease in amplitude immediately following the peak amplitude. Many sounds will also include a sustain, which is a length of time where the sound sustains a relatively constant amplitude. The sustain period is followed by a release. This is where the sound decreases in amplitude until it reaches silence again. When you put together the attack, decay, sustain, and release periods, we refer to this as the sound envelope. If you're looking at a waveform in your editing software, the sound envelope is the shape of any given sound in your timeline. This is useful to be aware of when you get into dialogue editing. Now, some sounds won't have all these elements. A sharp transient sound like a drum hit has almost no attack time because its full volume is reached almost immediately, and there may be little to no sustain. Timbre also includes things like microintonations. These are tiny changes over the duration of the sound in the fundamental frequency. Vibrato, which are fluctuations in the overall frequency during a sound, and tremolo, which are fluctuations in amplitude during the duration of the sound. Probably one of the easiest ways to demonstrate quality in a sound is to look at various musical instruments that are all playing the same note at the same amplitude. We can easily tell that the sounds are coming from different instruments because each instrument will generate a different quality as they play that note. In fact, even different makes and models of the same instrument will have unique quality aspects to them. Scientists have spent decades trying to understand the secrets behind Stradivarius violins. If we listen to the same note being played on a flute, a French horn, an oboe, a tuba, and a violin, we can clearly hear a big difference in the quality of sound these instruments produce. When we look at a close-up view of the waveforms from each of these sounds, we also see that difference in quality on display. Simply looking at these images would not suggest that we were looking at the same note being represented by each waveform. Okay, why don't we end things there for now? But come back next week and we'll continue our discussion on sound theory. Goodbye.